Hi everyone, my name is Jenny Durost. I think you can hear me now. Let me know in the chat if you can, just so that I don't keep talking to myself. We are going to start AP Calc mid-year review right now. So we're going to do some of everything. So what I want to say right now is that asking me to cover an entire semester of calculus in 1 hour is pretty much impossible. So I kind of want to gear it towards what you guys are looking for. So kind of give me some info as we go in the chat room. If we start talking about something and you have a question, ask it. If you want me to stop and go slower on something, say that. If you're feeling like we've got this, you can say that too. We can move on past some of the easier stuff, and I'm going to get to as much as I can. And if I don't get to everything that you need to, just know that you can give us some feedback about the things that you still want to see that I didn't get to, and we can definitely do another live stream to cover that stuff too. So basically what we're going to do today is a little bit of everything. So we're going to go through things real quick, but we are going to talk a little bit about limits. We're going to talk about taking derivatives, and we're going to do some derivative applications. I'm going to stick to things that I feel pretty confident that everybody's already covered. So hopefully that's the case. So we're going to start with our big idea number one, which is limits. We're not going to spend a ton of time on this, but just to kind of start, let's start with a question that gets to the basics of what a limit is. So if I tell you that the limit as x approaches a of some function f of x is equal to L, where L is some real number, which of the following things has to be true? I'm going to give you 1 second to think about that. You can type your answer into the chat room if you want. Just kind of, if you want, you can label them, 1, 2, or 3. All right, so Jonathan is on the right track, and hopefully some of you were thinking that as well. So kind of the definition of what a limit is what's happening to a function as you approach a value from the left and from the right? So we introduced the limit because up until now we've talked a lot about, well, we want to know what that function value is. So what's happening to the function at x equals 3? Well, now we've decided that maybe we don't actually always need to know exactly what's happening at 3. Maybe we want to know what's happening as we get close to 3. So that's what the limit is kind of approaching. So when we talk about the definition of a limit, we're talking about what's happening to the function as I'm coming from the left and as I'm coming from the right. And so that's number 1 and 2, right? Number 1 is the notation for the limit as x approaches a coming from the left. And number 2 is the limit from the right. And so what we're doing is, what is f of x getting closer to? It must be getting closer to L on the left and the right in order for there a limit to exist. What doesn't have to be true, though, is that the function itself does not have to equal L at that point. You could have a hole there, and that would still have a limit, but not a function. So then my next question is, if the third criteria is also true, what does that tell us? So the limit from the left and right gets us a limit, but what if we also say that the function at a actually equals L? What does that tell us about f of x? Right, okay, so f of x definitely exists because we said it equals L, and it's also continuous, right? So we would say that f of x is continuous at x equals a. So we don't really know about any other point of f of x, so we don't want to just say f of x is continuous. I know that's hard to type in the chat room, but we do want to be specific if this was a free response question, right, on the AP exam, that f of x is continuous at x equals a, because the limit from the left and the limit from the right and the actual value are all the same. That's our our calculus definition of continuity, which is a really important thing and almost always comes up in a free response question. I think in the last 12 or so years of free response questions, it's appeared somewhere in the free response question. How do I know that it's continuous? And the way we prove it is we have to say each of these things. We have to first say that the limit from the left is equal to something. Then we say the limit from the right is equal to something. Then we check and say the function itself is equal to that something. And if we can say that all three things are the same, then we get continuity. So limits are good for helping us find continuity. They're good for limit definitions. But another thing that you might have to use a limit for on the AP test is finding an asymptote. So we could have to find a vertical asymptote or a horizontal asymptote, and those are found in kind of two different ways. So a vertical asymptote, think about your graph here, right? Why can't you see what I'm writing? Sorry, my screen has stopped writing for you, and I don't know why. Well, that's not good. I'm going to try to X out of this real quick and see if I can get it back up. There we go. Okay. So, if I have a vertical asymptote, let's say there's my vertical asymptote right there, then generally speaking, the way an asymptote comes, that happens if our function is getting closer and closer and closer to it, but not touching, right? And it could be doing the same thing or different on the other side. So let's talk about how that would be described in limits, right? Think about what's happening. Let's say this is A. We have the limit as x approaches A of f of x. Okay. You're going to have two sides to that limit, and they're not necessarily going to match. In my picture, they don't match. They could both be going in the same direction. Doesn't really matter. But right here, we're going to know that if we check out the limit as x approaches A from the left side, it's going to be infinite, right? So I might write something like that. Your teachers may have talked to you about writing equals infinity. Generally speaking, that's kind of a weird thing because you can't really equal infinity since infinity is not a finite value. It doesn't have an equality. Usually, nobody's going to take any points off, or the AP test won't really take a point off if you write equals, but you don't want to risk that. So usually what I tell my students to do is say, it's approaching infinity because we can acknowledge that that's happening. It's called an infinite limit, but doesn't really equal infinity. I don't know. You can kind of talk to your teacher about their approach on that. But regardless, the limit itself is going towards infinity, right? And so that's the important part that tells us we have an asymptote. If your limit approaches infinity or negative infinity, then you're going to have an asymptote. So you could do the same thing on the other side. And so you get positive infinity or negative infinity or some combination of both. That's going to get you a vertical asymptote. A horizontal asymptote, right? That happens, that's end behavior. So that happens towards the ends of the function. remember we can actually cross the horizontal asymptote in the middle of the function, right? Horizontal asymptotes are not the same as vertical asymptotes. Vertical asymptotes you can't ever cross because they're outside of the domain of the function. But horizontal asymptotes you can technically cross the middle. But horizontal asymptotes are what we call the behavior. They're describing what's happening as we go to the end. And that gives you a hint for your limits as well, because the horizontal asymptote happens when you have end behavior. So what happens is you're approaching the infinities, right? So in this case, we would get the limit as x approaches infinity of f of x. And if that gives me a finite value, then I have a horizontal asymptote. So we could say that at y equals L, we have a horizontal asymptote. We also could check at negative infinity, right? That could give us the same horizontal asymptote or a different one. Your vertical asymptotes are going to have an x value. So x equals a is going to be your vertical asymptote. All right, well, let's see what else we got. And my screen is freezing again. Oh, no. There we go. All right, so the next thing we're going to cover is actually taking some limits. So unfortunately, there's a million little limit rules that we could talk about, and that I could spend the whole entire hour on that, and I don't want to. So I tried to pick some of the harder ones to talk about. Certainly, we could start with the basics of you to find a limit. The first thing you do, right, is you try to plug in the number. So you plug in the number. If you get an answer, then you're awesome. You've got your limit. If you don't get an answer, then you have to try to figure something out, right? So there's a few things that might happen. So let's see some of them as they pop up, okay? So this first one here, I want to know the limit as x approaches 2. I said from the positive side. We'll get to why that's important in a second. Well, let's start by doing our basics, right? The first thing we try is we try to plug in 2. So I'm going to try to plug in 2, and I'm going to get 4 minus 2 minus 6 over 2 minus 2. So obviously that equal sign makes me uncomfortable because negative 4 over 0 is not a number, right? That's undefined. So I definitely don't want to say that that's my answer. So we got to talk about what that means a little bit. So we've got an undefined, which we could say that the function is undefined at that point, right? That's what we've decided because we've plugged the value in. The function itself is undefined. And we can see that too in that denominator. So the denominator is definitely going to give us a 0 when we plug in 2. So that means that that's not in the domain of that function. But it might still have a limit because a couple things can happen in these rational functions. We can have an asymptote, at which point we wouldn't have a limit. It would be infinite. Or we could have a hole. So what we need to check for right here is it a hole? And if not, is it infinity? So there's a few strategies that we can do. We can try to see if we can plug the hole. If we plug the hole, that usually comes from something on the top and something on the bottom canceling. So we might want to try to factor and my screen is delayed, but if you go ahead and try to factor that, right, that top, you're looking for two numbers that multiply to be negative 6, add to be negative 1, so we get x minus 3 and x plus 2. So that's our factoring on the top. So you notice nothing's going to cancel. If the top had an x minus 2 in it, we would cancel those out, we'd have a hole, and we'd be good. But we don't. So that strategy is not going to work. So that generally means since it's not a hole, it's going to be an asymptote. The important part, though, is my function going towards positive infinity or is it going towards negative infinity, right? We got to figure that out. So that's where this x approaching 2 from the positive side is going to become important, right? Because I want to know that if I'm on coming from the positive side, I got a little graph here, here's my 2. I'm going to come in it from this way, right? So I might have 2 different answers on either side. So the side is going to matter. So we know it's probably going towards infinity or negative infinity. We need to decide which one. And so we're going to kind of pay attention to the sides, right? So we've already decided that if we plug in 2 on the top, we get -4. On the bottom, we get 0, okay? But we can't really get 0. So we want to know what's happening when we get closer and closer and closer and closer and closer to 0, but not touching it, because that's what a limit is. So we do 2 minus, so our function is x minus 2. So the 2 that we're plugging in for x is actually coming from the positive side, right? So we're actually plugging in a number that's really close to 2, but a little bit bigger than 2. So we might be plugging in like 2.0000001, right? Something that's really, really close to 2, but a little bit bigger. If we plug in a number that's a little bit bigger than 2 and then subtract 2, we get a number that's a little bit bigger than 0. I always kind of tell my kids to call that like 0 positive, right? A number that's a little tiny bit bigger than 0. So on the top, we have -4. On the bottom, we have 0, but we have a number that's a little bit bigger than 0. It's really close to 0, but it's a little tiny bit bigger than 0. And that is going to give me a number that is huge, but negative. So that means that this whole thing here becomes negative infinity. Okay. So that's the first one. I'm going to move now to the one to the right of it. Okay. So in this one, if we plugged in 3, I'm going to go ahead and give you the surprise, right? If I plugged in 3, I would get 0 on the top. I would get 0 on the bottom. When I learned calculus a long time ago, and what I tell my students is 0 over 0 means do more work. It doesn't mean necessarily that it's undefined, like the first one did. It means that it could be undefined, but it also means that we just need to do more work. We have no conclusion yet. So when you get 0 over 0 for plug-in, that means do more work. We already talked about factoring. Factoring is one of the most common ways to do more work. Another one is to use multiplying by the conjugate, which is what we're going to use here. That helps us get rid of any square roots if we have square roots. So I'm going to take this one and I'm going to multiply by the conjugate. And hoping that that's going to get me the more work that I need to see if this actually has an answer. So on the top, we're going to get those square roots to cancel out. Now, before today, or before you probably learned this, you might have really only used that method to get square roots out of the denominator because that's how we rationalize functions. We can use it in the numerator or in the denominator. It doesn't matter. If we want to get rid of the square roots to try something to see what works, we can do it in the numerator or the denominator. So in the numerator, I'm going to get x plus 1 minus 4. And then in the denominator, I'm going to go ahead and just leave that the way it is. And my reason for that being I kind of know that we're hoping things are going to cancel out. So I'm going to leave it factored just so that we can see if anything factors. And hopefully you can see that this numerator is going to be x minus 3, right? So that numerator cancels with the x minus 3 in the bottom. And we're left with me out of room, but limit as x approaches 3 of 1 over root x plus 1 plus 2. And then once we get that to pop up on my screen, we can plug in our 3 again, right? And this time we'll get an answer. We plug in 3 we get 1 over root 4, which is 2 plus 2. So we should get 1/4. On the bottom, I have an example of a limit at infinity and a sine x over x problem. So those are two other kind of ones that come up a lot that are a little bit weird. So infinite limits, 3 things can happen. I only put 1 on here, but there's 3 things that can happen. So the limit can go towards infinity or negative infinity itself. That usually happens when the numerator is bigger than the denominator, right? If the numerator gets big super fast and the denominator gets big slower, then the whole function will go towards infinity or negative infinity, depending on the sign. The other thing that can happen is that the function goes to 0, right? And that would happen if the denominator is bigger, right? So if we have x to the 4th on the bottom, but only x squared on the top, that denominator is getting bigger so much faster that it's going to get big fast. The top is going to be getting big slow, so we get 0 altogether. So those are 2 of the things that can happen. The third thing happens that the top and the bottom are growing at roughly the same rate. And that's what's going to happen in this problem here. I have an x cubed is my dominant power on the top. And that's going to grow at, we're talking about infinity cubed. One thing that we want to kind of pay attention to is that when we talk about doing powers of infinity, infinity is huge, and then we're cubing it. That's super huge. Whereas infinity squared, also super huge, but not nearly as super huge as that infinity cubed. So the infinity squared and the plus, especially the plus 1, the plus 1 is going to do nothing when you're up at infinity, right? It makes no difference. But even the infinity squared isn't going to make a huge difference because it's so much smaller than infinity cubed that it doesn't have a super large impact on my problem. The denominator is going to follow the same pattern, right? I could distribute that x squared out, and I would get x cubed, 3x cubed, plus 4x squared. And so, yep, so Jonathan just said, don't we have to distribute? Yep, that's what we're doing now. So, yeah, I was talking about the numerator first and then hadn't talked about the denominator yet, okay? But so in the denominator, we are going to distribute. And again, we're going to get an x cubed is our dominant kind of power there, right? That infinity cubed is going to be so much bigger than that infinity squared. But what happened now is our numerator and our denominator are roughly the same size, right? They're both infinity cubed. The infinity squareds don't matter. The plus 1 doesn't matter so much. But we do have an infinity cubed and infinity cubed. So they're a little bit closer together. So when we talk about that, we have to look a little bit more closely to what that limit is going to be. So what I kind of tell my students is you can think about it as the rest of those things don't matter so much, but the 2x cubed and the 3x cubed do matter. Those are the 2 things that are going to determine what our limit is. And since they're the same side, those coefficients are going to matter. So the x cubed and the x cubed are going to kind of cancel each other out, and you're going to be left with 2/3 as your limit. Okay. So if the top is heavy, right, if the top is bigger, a lot bigger, then you get infinity. If the bottom is a lot bigger, you get 0. If the degrees are the same, or if the whatever functions you're using are of equivalent size, then the coefficients start to matter again. And then we have the limit as x approaches 0 of sine x over x. I'm going to do this real quick because I want to get to derivatives, and I also want to get to composition of limits, and we're already almost halfway through our time. So you need to have memorized, you probably learned it through maybe the squeeze theorem, sine x over x. Usually that's how teachers teach it, but I don't know. The limit as x approaches 0 of sine x over x is a limit that you just kind of have to know. A weird one, so you have to know it. And that is equal to 1. And so a lot of times we try to manipulate that by finding a limit that's related to it. And the way we do that is we just we make things happen, right? So we have sine x over x right here. That's going to equal 1. This one's pretty easy because there's just the 3 out front. So if sine x over x is 1, the 3 is in the bottom, you get 1/3 as your answer. They can do some funky things by putting the 3 inside of the sine, and then you just have to make sure that it matches with the bottom. But we can do more of that on another day if you guys want to. I'm going to skip this one because it's kind of easy. Let's do the super hard ones. So this is new this year. I mean, obviously you guys have not taken AP Calc before, but I've taught it before. Yeah, it's definitely going to take more than an hour, but we're going to do what we can. So the idea here is composition of limits, and these ones are kind of weird. It wants you to start to think about things that are different than your standard plugins, your standard looking at a graph and finding the limits. So I'm just going to give 2 kind of hard examples here. So this is the limit as x approaches 0 of f of h of x, and I've given you graphs of f of x and graphs of h of x. So normally when we find a limit, right, we look at a graph. So if I was going to find the limit as x approaches 0 of h of x, right, that inside function, I would go to my graph and I would look and I would find what's happening as I come from the left and I come from the right of 0. And hopefully you see my pen is delaying again, but you can see that it's approaching 2, right? As I come from the left and right of 0, h of x is approaching 2. Easy enough, right? So, but then what I actually want to find, though, is I want to find the limit as x approaches 0 of f of h of x. So I already plugged in the h of x part. So now what I'm really finding is the limit as x approaches 2 of f of x, right? Because my input is now 2. My input was h of x, but now I found that my input is actually 2. So I'm finding the limit as x approaches 2 of f of x. So now I look at my f of x graph, and I'm looking at the left and the right of 2, and I find that I actually have 2 different answers. So in most cases, we would say, oh, well, the limit as x approaches 2 of f of x is actually, it doesn't exist, right? Because the left side and the right side don't agree. So we're stuck, right? We have the left, we have the right, they don't agree. Case closed, doesn't exist. Except for that's not quite true here. Because with the composition of functions, there was something about our first function that we didn't pay attention to. So let's go back to h of x. The limit as x approaches 0 of h of x, we said it was 2, but let's look at that 2 a little bit closer. When I'm coming from the left of 2, I'm coming to 2, but I'm coming to 2 from below it, right? So I'm coming from 2 from underneath. When I'm coming from the right, I'm also coming from underneath. So both directions, I'm actually coming from underneath 2. So my values are always a little bit smaller than 2. They're never a little bit bigger than 2. They're always a little bit smaller than 2. So when I go to my second limit, I actually only care about the limit as x approaches 2 from the negative side. I only care about the function as I'm coming from a little bit smaller than 2. Because h of x never is coming from above 2. It's always coming from below. So our new limit is actually the limit as x approaches 2 from the negative side of f of x, which does have a value. It has the value of -1. So absolutely, Sebastian, if both were coming from above, it would be as x approaches 2 from the positive side, right? And if they were coming from different directions, it would go back from being, we don't know, right? It would be undefined. But because they're coming from the same direction, we have a limit that we actually can find, which is pretty cool. And that has never been on the AP test before. It's new this year, which is actually cool because it gets you to think about things a little bit. because of direction. Okay. So I'm going to give you another example that's different, but kind of the same idea, because these are a little bit tricky. If you haven't done a lot of these, they are in the AP Classroom this year. You can ask your teacher to open that up for you. At the end, I'll give you my school email address. And if you send me an email, I have a whole bunch of practice ones of these too. If this is something that you're like, oh, I've never seen that and I want to practice that, okay? So this one is a little bit different, but the same idea. It's confusing because direction is going to matter. So this one, I want the limit as x approaches 2 from the negative side of g of 10 minus x squared. So the first thing we kind of do, right, is we plug in the 2 for x squared, right? And we can simplify this to the limit. Well, we'll get to that in a second. So if I plugged in 2, I would get 4, 6, right? So this is kind of the same as saying the limit as x approaches 6 of g of x, right? Because if I plugged in 2, I would get 10 minus 4 is 6. So I'm changing my limit to say now the limit as x approaches 6 of g of x. But you probably have a hint that direction matters, right? Because the direction was in the original problem. Direction is in my new problem. So this one, though, what you have to be careful of is if you plug in a number that's a little bit smaller than 2, right? Then when you square it, you get a number that's a little bit smaller than 4. So if I get a number that's a little bit smaller than 4, then when I do 10 minus a number that's a little bit smaller than 4, I actually get a number that's a little bit bigger than 6. Let me walk through that one more time just so you can follow it, right? So in this here, I'm plugging in a number that's a little bit smaller than 2. When I square that number, it's a little bit smaller than 4. So when I do 10 minus a number a little bit smaller than 4, I get a number that's a little bit bigger than 6. So when I take this limit, I'm actually looking at the limit as x approaches 6 from the positive side, because I want a number that's a little bit bigger than 6 of g of x. So you look at my graph, that's going to be that side, right? And so I get 5 as my answer. So these two are just examples of some kind of tricky limits where you have to really pay attention to direction and what the equation is actually telling you. Is the number both sides, or is it always smaller, or is it always bigger? What direction am I coming from determines the answer to your question. All right, let's move on to derivatives. Whew, finally, okay. So the big thing that we need to walk away from derivatives, and we're going to talk about all kinds of derivatives in the next half hour, but is derivatives are basically slopes, right? So in Algebra 1, we learned how to find the average rate of change, right, between two things, mostly with lines, but we could find it for other things. As we moved on, we're now talking about, I don't want an average rate of change anymore. I want an instantaneous rate of change. I want to know what the slope is at a single point. That's what the derivative is. So we do all kinds of things with derivatives, but it always comes back to, can I find the slope of that curve at that point, or the slope of the tangent line at that point? A little picture of that. It's going to come up in a second. But this picture is, right, the average rate of change. If I were able to take that red dot and move it closer to the black dot, right, my average rate of change would get more accurate. And if I could make it exactly on top of that black dot, then I would get the instantaneous rate of change of that blue function right there. And that's the limit definition. I'm not going to do any limit definition problems with you because they take a long time, but that's another thing that if you want to practice on, you can give that feedback and we'll try to fit that in somewhere. So first thing I want you to do is I want you to take the next 30 seconds and see if you know the derivatives to all these functions, because that ultimately is going to be the most important thing that you can do in derivatives, is know what we call our one steps. If I look at a function, do I know its derivatives? I'm going to give you 30 seconds, and I want you to see if you can write down all those derivatives for me. You can do it in the chat, or you can just do it on paper and test yourself. You don't have to. Writing it out in the chat would take a long time, probably. So just, if you have scrap paper by you, just write them down real quick, test yourself. All right, let's see how you did. I had to squeeze some of them in there a little bit, but here's your 1 steps. So these are things that you actually, you need to know them like your back of your hand. You just need to know them. I give my students time tests like they were in 3rd grade, right? When you did the multiplication ones, like 6 times 7 is 42, and you had to do it fast. I do that with my kids just to get them used to making sure that you can take these derivatives and you can take them quickly, and that you know them really well. So if you weren't able to kind of produce them quickly, that's something that you definitely need to study, because we're going to use them all the time throughout the whole year, and they need to be like the thing that you definitely know. These are the ones that are the most common. These are the ones that at this point I would expect you to know. There are more. So you may or may not have seen these ones. These are the other ones that are on the AP test. If you haven't seen them yet, though, I wouldn't stress about it. Your teachers will show them to you eventually. They're not used nearly as commonly, but there are some more in case anybody wanted to see them. So let's talk about, there's 3 rules to taking derivatives, okay? The product, the quotient, the chain. I'm going to show you how I take them. They are a little bit of a pain. I'm going to make them easier for you. So if you've watched me teach this, or if you've watched Jamil Siddiqui teach this, I know, and Suzanne Farrellock also worked for Fiveable, we all do it the same way, but your teachers might not. So this trick might help you a little bit. I'm going to change the problem a little bit, and I'm going to get rid of that 3 just for now, because that makes it a chain rule, and we'll talk about that one in a second. Oh, yeah, these ones, those are a pain. So let's do product rule. So product rule, there's this big fancy rule, right? It says that f prime of x is equal to, or sorry, let me write this better. It basically starts with if h of x is f of x times g of x, then h prime of x is going to be f prime of x times g of x plus g prime of x times f of x. If you're anything like me, you have to, I don't know, I have to think about that a lot every time I say it. Even as I was writing it down, I was like, I hope I got that right. So I like to do it visually. That helps me. So I make myself a little table. And in my table, I'm going to put my 2 functions. So basically, I have f of x on one side, I have g of x on the other, right? And now I'm going to take their derivatives. So the derivative of 2x is 2. The derivative of sine x is cosine x. And I'm going to put that in my other boxes. So then if you look back to my rule, right, it says f prime of x times g of x. That's this diagonal right here. So I'm going to start by saying that I've got 2 sine x. And then if I look back to my rule again, I put a plus in the middle. And then my second part is the other diagonal. So if you happen to like that visual approach better, go ahead and use it. No AP grader is ever going to look at that table, but if it helps you organize your thoughts, then go ahead and use it. But that is how we get our derivative. And it's basically just a visual way to represent that same formula. Quotient rule is the same thing, okay, except for this time you have a minus, right? And then you have the original denominator squared. So that's the part that everybody always forgets. And honestly, I have no tricks to help you remember that. I usually just tell my kids that's the part you do first. I always say, all right, let's start by writing that down as step number 1. Because that way, no matter what we do to get the work done for the rest of it, we don't forget that part. Because that is usually what you forget after you do everything else. So I'll put that there. I can make the same table for quotient rule. Take the derivatives, right? 3x squared becomes 6x plus 1. And then the same idea, right? We're going to take that criss and cross, right? You always start in the bottom left, do a diagonal. And then this one's subtraction, and you can do the other diagonal. Sorry, that's really messy, but that's the quotient rule. For time's sake, I'm not going to bother simplifying that. Obviously, if this is multiple choice, you should. If it was free response, don't bother, right? But it does simplify, but we're going to leave that alone. Let's do the chain rule. Okay, the chain rule basically has 3 steps to it. I gave you an incredibly hard chain rule to start. I don't know why, but the chain rule has 3 steps, okay? The first step is take the derivative of the outside. So what I usually tell my students is first you want to determine what's the outside and what's the inside. We start all the way outside. So my outside function is what I like to say something squared, right? The squared part is the outside function. The something inside doesn't really matter right away. So the first thing you want to do is take the derivative of the outside. So you get 2 times something. And that's literally what I say to the kids, and I have them repeat it back to me. What's the derivative of something squared? 2 times something. Because that helps us remember step number 2, which is just to copy the inside. Whatever was the inside before is going to still be the inside. So we had 2 something, and we're going to copy that whole mess. I probably didn't leave myself enough room here, but we're going to copy that whole inside right back into our function. That's step number 2. Then step number 3 is the derivative of the inside. So step number 1, derivative of the outside, copy the inside. Now we're going to take the derivative of the inside. Now, this unfortunately is going to present us with another problem because it's going to be another chain rule. So I need the derivative of the inside here. The inside we're saying is this secant square root of 4x squared plus 2. But that's actually going to give us another chain rule because we still have another outside and another inside. So we're going to go through our 3 steps again. So step number 1 is derivative of the outside. Outside function is secant something. So the derivative of that is secant something, tangent something. Step number 2 is copy the inside, right? So our inside is square root of 4x squared plus 2x. Sorry, there's a delay again. But that's the copy the inside part. And then we get to step number 3, which is derivative of the inside. So we need to take the derivative of the inside again. This is going to be another chain rule. I don't know. I gave you a really hard one to start with, right? But I'm writing those green lines there to show that I know that I need to take the derivative of the inside. I need to take the derivative of square root of 4x squared plus 2x. That's what I need to take the derivative of right now. And I'm going to put that into the green line. The problem is it's another chain rule. So I got to take its derivative. So now I have my outside function now, right? Because this is what I'm dealing with. I need to take the derivative of that, the 4x squared plus 2x. So my outside function, right, is something to the 1/2 power. So that becomes 1/2 something to the negative 1/2. Oops, I should have done that in red. Sorry. Copy the inside. And now derivative of the inside. And thankfully, we can now just do the 8x plus 2, right? We got a derivative of the inside. That's not a chain rule anymore. Now, again, this is certainly a problem that could use a whole lot of simplifying, but I'm not going to take that time to do that right now. But we certainly could if we wanted to. Okay. So we did product rule, we did quotient rule, we did chain rule. Those are the 3 ways of taking derivatives in just x's, right? But we can also do derivatives with x's and y's. If you have a second in the chat room, let me know if you've covered implicit differentiation yet. A yes or a no is good. If the answer is no, then I might skip it and come back. But if you have, we can go through it kind of quick. So the idea between implicit differentiation is that you now have to take a derivative in 2 variables. And we don't necessarily have functions anymore where we had a function before, f of x equals something. This is no longer a function. So the rules are a little bit different. When we take these derivatives, we're going to kind of do it the same way. And I'll kind of show you how I go through that. The derivative of x, right, is still going to be 1, same as it's always been. Now, the problem comes with the sine y, right? Because we would think that maybe the derivative is cosine y, right? And you'd be kind of right. The derivative is cosine y. But when we take the derivative, right, remember we have this expression, the dy over dx. It's popping up in a second. It's delayed again. Dy over dx means I'm taking the derivative of y in terms of x. So when I take my derivatives, I'm always taking it in terms of x. Well, y is a function. Y is not necessarily a function, but y is a variable that's dependent on x. So when we take the derivative of y, we need to kind of treat it like that chain rule we just did, where we take the derivative of the outside, right? So the derivative of sine is cosine. We got that part right. We copied the inside. But now we need to multiply by the derivative of the inside. Well, the derivative of the inside is the derivative of y. So you can write that as dy over dx. You can write that as y prime, whatever. It doesn't matter really. But you have to add that part in or multiply that part in, right? Because this is a chain rule. It's cosine of y times whatever the derivative of y is. And the derivative of y is what we're actually looking for in this problem. So that's going to become important later on. And then on the right-hand side, we have a product rule. So I like to do my little product rule chart here. The derivative of x is 1. The derivative of x is actually dx over dx. Okay, so it's not that we're treating x differently. It is dx over dx, but that's just 1, right? So that's why we don't write that ever. Whereas y, we do have to write that because that's not 1. So I do my crisscross and I get y plus x dy over dx. And then your goal is going to be to get dy over dx by itself, right? That's implicit differentiation. Your goal is to find the derivative. So your goal is to get the dy over dx by itself. So it's kind of almost always the same thing, right? You want to get all the dy dx's over on the same side. And then you can factor it out. And once you factor it out, then hopefully you can see that to get it by itself, you just have to divide, right? So that's implicit differentiation. So we've now actually we've covered a lot. We did all those limits, some hard ones. We've covered all of the basic rules of derivatives. What's left is some derivative applications. We're not going to probably get very far with this before we have to stop, but we covered a lot, so that's kind of cool. When we get to the derivative applications, now we're talking about what the derivatives tell us. So I came up with a whole list of things that I think that you at this point should know about what f prime of x tells us about f of x. So hopefully at this point you know that if f prime of x is greater than 0, that means that f of x is increasing, right? Since f prime of x is the slope, if the slope is positive, then the function is increasing. If the slope is negative, then the function is decreasing. Some vocabulary there. If f prime of x is equal to 0, I should actually have put in also or undefined, right? If f prime of x is undefined, you also have a critical point, same as 0. I did put that in the next line, sorry. A critical point is a horizontal tangent or a vertical tangent, and sometimes it's a max or min. It's not always a max or min. So we do call it a critical point, but just knowing that the derivative is equal to 0 is not enough to tell us that it's an extrema. Okay, so we got to check for further things there. You know it's a relative min if the derivative is 0 or undefined, but it's changing from positive. Sorry, I got that backwards, didn't I? It's a no, I just wrote the wrong word. So that should be maximum there. F of x is a relative max if f prime of x is changing from positive to negative. F of x has a relative minimum if f prime of x is changing from negative to positive. So we're not going to do a lot with this because we're going to run out of time, but what you want to do is when you find a critical point, you then check the signs on either side to see if it's changing. If it's changing, then you know you have a max or a min. The second derivative tells us about concavity, right? So if the second derivative is positive, that tells us that f of x is concave up. If f double prime is negative, then f of x is concave down. If it's 0 or undefined, then f of x is a potential point of inflection. But again, it's not a point of inflection until it changes sign, right? So if the f double prime of x is 0 undefined and changes sign, then we have what we call a point of inflection where the concavity is changing, right? So I think I'm going to end with this problem right here. Okay, so this is a would probably be a calculator problem if you had to find x and y intercepts. But depending on what you have to find, it may or may not be a calculator problem. And I said, tell me everything you can about this function. Now, for time's sake, we're going to cut it short, and we're going to talk just about the calculus part. So what you first could find was x and y intercepts, right? You could set the function equal to 0 to find your x-intercepts. You could plug in 0 for theta, or sorry, your theta intercepts, right? You plug in 0 for theta to find your y-intercepts. That could happen. That's not calculus, though, so we'll skip that part. And we'll start talking about what the derivative tells us. Okay, so the derivative we're going to start by taking that. And you should get that -2 sine theta, right, would be the derivative of the first part, and then -1 would be the derivative of the second part. And there's a delay, so it's not showing up, but hopefully it will in a second. So our goal then should be to find when the derivative equals 0. Because if we can find when the derivative equals 0, then we can find Hi guys, I'm sorry about that. I am back. So if you want to hang around, I can finish that last problem for you. If not, you can check out. Let me just get my screen back up here. Right, almost there. What? Oh, sorry guys. There we go. All right. So yeah, if you want to hang out for a few more minutes, I will certainly do this last problem with you. I don't know exactly when I cut off, but we were taking the derivative of this function here to find when the derivative was equal to 0, right? So I took f prime of theta. I got negative 2 sine theta minus 1. And then I set that equal to 0, right? When I set it equal to 0, that's going to give me my potential critical points. So that's what I'm looking for first. So when I do sine theta equals negative 1/2, I'm looking for the values between 0 and 2 pi that was written in the domain there, where sine of theta equals negative 1/2. So that happens, right, when the opposite side is negative 1, the hypotenuse is 2. Little trig review here. So those two triangles are going to be 30, 60, 90 triangles. In radian land, that's pi over 3 or pi over 6. Since the opposite side is the smallest side, that means these are pi over 6s or 30-degree angles. And that's going to be the 7th pi over 6 and the 11th pi over 6. I know my students always kind of are a little rusty on their trig. I notice I have one here. Davina, hey, what's up? So if you need refreshers on trig, that's a great thing to review. And you can request that too as another screencast, okay? So we've got theta equals 7 pi over 6 and 11 pi over 6. Those are our two critical points. Those are our potential maxes and mins. Those are when the function could be changing whether or not it's increasing or decreasing. So another thing that I do, which may be different from your teachers or maybe the same, is I make myself a little number line as a visual way of representing what's happening. So I know the only place that my derivative could potentially change signs or where it equals 0 is at 7 pi over 6 and 11 pi over 6. So what we're going to do is we're going to check the signs on either side of that. So before 7 pi over 6, if I look at my derivative, right, so I'm going to go back to my derivative, and I want to know what's happening before 7 pi over 6, I'm going to pick a nice, easy value to plug in. Nice, easy values are like 0, right? 0 is a nice, easy value. So if I was at 0, and I plug that into sine, I get 0. 0 times negative 2 is still 0. Minus 1 gets me a negative number. All I really care about is that it's negative. I don't really care what its actual value is. I just care if it's negative or positive. Because if the first derivative is negative, then I know that my function is actually decreasing. So I know something now. I know that my function is decreasing between 0 and 7 pi over 6. Between 7 pi over 6 and 11 pi over 6, I want to know what's happening there. The easiest number to plug in there would probably be 3 pi over 2, right? If we plug in that axis, we know that's in between those two triangles. And we know that sine of 3 pi over 2 is negative 1. So I can kind of remember my little sine curve here. Sine of 3 pi over 2 is negative 1. So if I plug that in here, I get negative 2 times negative 1 is positive 2. Minus 1 is positive 1, so I get a positive value there. So now I know my function is increasing. If the derivative is positive, the function is increasing between 7 pi over 6 and 11 pi over 6. And then I need to check something on the other side. So I can go to 2 pi, right? Sine of 2 pi is 0 times negative 2 is still 0. Minus 1 gets me a negative. So now I know a bunch of things, right? And I know that, see, f of x is decreasing. We're going to start at 0 because that's where our domain starts. And 0 is not included in that interval in the direction, so we're not going to include it in our interval here. If it was included, we would include it. But because it's not in the domain, we're just going to not actually include it. And then it stays decreasing to 7 pi over 6. We can include that one. And then it also decreases from 11 pi over 6 to 2 pi. And we can say that is because f prime of x is greater than 0. So you wouldn't want to do quite this much shorthand on an actual AP test. You'd want to write out the word decreasing and the word because, but for this purposes, I'm going to shorthand it a little bit. But that's kind of what we're looking for, right? F of x is decreasing on 0 to 7 pi over 6 and 11 pi over 6 to 2 pi because f prime of x is greater than 0. F of x is increasing on 7 pi over 6 to 11 pi over 6. Because f prime of x is less than 0. You can also say there's a minimum, right? At 7 pi over 6. And the reason for that is because f prime of x is equal to 0 and changing signs. Okay, again, that's a lot of shorthand you don't want to actually use, but we have a minimum at theta equals 7 pi over 6 because f prime of x equals 0 and is changing from negative to positive at that point, right? Sorry, that should be a theta, not an x. And then you could write the same thing for the maximum, right? There's a maximum at 11 pi over 6 because f prime of theta is equal to 0 and it changes from positive to negative. So that's all the things the first derivative tells us about the function. The second derivative tells us some information too. So I'm going to go ahead and take the second derivative. And we get negative 2 cosine theta. And we can set that equal to 0. Cosine theta is equal to 0 twice in that interval at pi over 2 and 3 pi over 2. So I'm going to make another little number line here. And I'm going to check some signs on each side of pi over 2 and 3 pi over 2, right? So over on the 0 pi side, cosine would be 1 times negative 2 is negative. Between pi over 2 and 3 pi over 2, cosine is actually negative. Now that we have this graph here, actually, that's helpful to us, right? Between pi over 2 and 3 pi over 2, cosine is negative. I multiply that by negative 2, I get a positive. And then the right of 3 pi over 2, I get positive numbers times the negative 2 is negative again. So this tells us that our function is concave down between 0 and pi over 2, concave up between pi over 2 and 3 pi over 2, and then concave down again between 3 pi over 2 and 2 pi. It gives us 2 points of inflection, right? Pi over 2 and 3 pi over 2 are both points of inflection because the signs are changing. And kind of gives us a nice idea. So we could write, I'm not going to write all of that out, but we certainly could write something down. F of x is concave up. Between pi over 2 and 3 pi over 2, because f double prime of x is greater than 0, right? So something like that we could write out. We could write out something similar for the concave downs. We could identify pi over 2 as a point of inflection because f double prime equals 0 and is changing signs. And we could actually get a decent rough sketch of our graph. So we now know if I'm going to combine those two number lines together, let me do that a little bit. Oops, that doesn't look good. So let's see what's happening in our number line. So we start with 0 at pi over 2. So between 0 and pi over 2, if we go back and we look at f prime of x, right, our f prime of x is negative and our f double prime of x is negative. So we have a decreasing concave down function. Between pi over 2 and 7 pi over 6, we now have we still have negative for the first derivative, right? So it's still decreasing. But now we're concave up, right? Because we're after pi over 2. So between pi over 2 and 7 pi over 6, we're decreasing concave up. Between 7 pi over 6 and 3 pi over 2, we are now in the first derivative is positive, so we're increasing. And we're still concave up because we're between pi over 2 and 3 pi over 2. And then after 3 pi over 2 to 11 pi over 6, we're concave down. And we are still increasing. And then the last interval, we are decreasing and concave down. So that actually could get us a pretty good sketch. We didn't find the x and y intercepts. If we had the x and y intercepts, we could get a very good sketch. We didn't. I skipped that part, so that kind of messes things up. But we do know that we're decreasing concave down. Let me see if I can move some of this. So we start with decreasing concave down. So that's going to look something like this. And then we're decreasing concave up. Probably not a sharp turn, but Nope, that's increasing. I don't know what I just drew there. Let me get rid of that. So decreasing concave up would look like this. This is better, right? Then increasing concave up. Then increasing concave down. Then decreasing concave down, right? So we could get a rough sketch. And if I had the X and Y intercepts, I could actually put that on an axis, right? I don't, so I can't. But you can kind of get a nice rough sketch of what's happening just by looking at that number line, right? So that is what f prime of x and f double prime of x tell us about our function. The only thing that I really wanted to get to that we didn't is related rates, which is kind of a shame because that's a big idea, but it is definitely past 9 o'clock now, so I'm going to let you go. We can certainly do some more related rate practice if you want, so just request that in the feedback. And I'm going to end it here. I did tell you that I would give you my email. I forget why, but oh, it was for extra practice with those limits, right? So I work at Grafton High School in Massachusetts. So if you want extra practice on any of this stuff, actually, if you just want anything, just send me an email and I will send you whatever I have that can help you out, and I would be happy to do that. If you do want some related rate practice, or if you want more practice of anything we covered, or if you think, oh, she didn't cover this and I really would have liked to cover more of that, leave some feedback, send me an email, leave feedback on Slack or on any of the Fiveable social medias, and we'll get that practice for you. So thanks so much for coming, and thanks for staying 18 minutes late, and I hope that that really helped a little bit, and I will hopefully see you guys again soon. Thanks so much.